Converting into the standard form is a direct process. If you properly apply the rules of distribution and combine your like terms, you'll achieve the desired result. In this video, however, we'll be converting from the standard form into the factored form, a process that's often referred to as factoring. And this type of conversion is an inverse process, which means that it undoes, or is the opposite of, a direct process. You can see several other direct and inverse process pairs here. Notice that inverse processes are more challenging than their corresponding direct process. And as you move to more complex direct processes, the complexity of their corresponding inverse processes also increases. That might be an indication that converting from the standard to the factored form will be a challenge. But if we focus on the direct process of converting to the standard form and observe some patterns that occur while doing so, we'll be ready to undo that process in no time. So let's get to it and do some factoring. While there are many tips and tricks for factoring, the best way to develop a deeper understanding of this process is to have a solid foundation in the process of converting into the standard form. So to continue building up that foundation, let's take some time to observe some patterns as we convert into the standard form. Let's start with these examples of the factored form, where the coefficient of the linear term in each factor is 1. And before we even convert them into the standard form, you might notice some patterns with how these problems are organized. Given that u and v are positive numbers, this entire first column is in the form of x plus u times x plus v. The second and third columns are in the form x plus u times x minus v. And the final column is in the form x minus u times x minus v. With that observation in mind, let's rewrite each example in the standard form. Now that we can see the standard form for each example, let's start with some overall observations. The first thing to notice is that the double distribution for these examples always resulted in 4 total terms. And those 4 terms were quadratic, linear, linear, and constant. And then, after combining the 2 linear terms, we always ended up with 3 terms. Next, observe that every result starts with x squared, since our double distribution process always starts with x times x. Then, let's look more closely at those constant terms. Since our double distribution only resulted in 1 constant term, we know that the constant term in our result always comes from the product of the 2 constant terms in the linear factors. For example, 7 times 11 is 77, 14 times negative 2 is negative 28, and negative 9 times negative 5 is positive 45. And finally, the coefficient of the linear term in our result is the sum of the 2 constant terms in our linear factors. For example, 1 plus 10 is 11, 4 plus negative 6 is negative 2, and negative 12 plus negative 3 is negative 15. Next, let's make some observations about individual columns. In the results of the first column, all of the linear and constant coefficients are positive, which shouldn't come as much of a surprise since the constant terms in the factored form were all positive as well. Then, in our second column, our linear coefficients are positive, but our constants are negative. The constants are negative because one factor in each example had a plus sign, while the other factor had a minus sign. And a positive number times a negative number yields a negative result. But why was the linear coefficient positive? Well, notice that in each example, the factor with a plus sign had a larger number than the factor with a minus sign. So when these two numbers were added together, while combining like terms, the result was still positive. Our third column is quite similar to the second column, but notice that in each example, the factor with a plus sign had a smaller number than the factor with a minus sign. Thus, the product of these two numbers was still negative, but the sum was also negative, unlike the second column. In our fourth and final column, the linear term of each result has a negative coefficient since both of the original factors had minus signs. But since a negative times a negative is positive, the constant term in each result was positive. The reason for all these observations is that when we start with the standard form, we'll want to know which of these categories the factored form will fall into. Take this quadratic, for example. Since the constant here is negative, we know that the factored form will fall into one of these two categories. And since the linear coefficient here is positive, that narrows it down to just this option. Thus, we know that the factored form of this quadratic will be x plus a number times x minus a number, where the number after the plus sign is larger than the number after the minus sign. With those patterns in mind, let's get to some factoring. We'll start things off with this example, and our goal is to find a quadratic in the factored form that's equal to this expression. So, how should we go about doing that? Well, we're essentially going to make a guess at what we think the factored form is, and then we'll check to see if it's correct. This is called the guess and check method, and is a common way of completing an inverse process. The issue with guessing and checking is that it can take a long time if we don't put any thought into our guesses. But thanks to the patterns that we just observed, we have plenty of information to inform our guesses. We'll start with this template. Notice that we put an x inside each set of parentheses, since x times x will be the only way for us to get the x squared that's in our original expression. In fact, this video will only look at quadratics that have a leading coefficient of 1, so this will be the template that we start with in every problem for this video. Next, we need to figure out what signs we should include with each factor. And since we want our linear and constant terms to have positive coefficients, we know from the patterns that we looked at that both of our factors should contain plus signs. Finally, we need to fill in the remaining spaces with numbers. But how can we narrow down our choices for our numbers? Well, when we multiply these two numbers, we should get the constant term from our desired result. Thus, we need to find two numbers that multiply to 12. In fact, let's just list out every pair of numbers that we can think of that multiplies to 12. And once we get to 3 times 4, we can stop. You might think that we could list 4 times 3 as our next option, but in this case, that wouldn't be any different from 3 times 4. From here, let's try out some of our numbers. We'll start by putting 1 and 12 into our blank spaces, but when we multiply that out, we don't get the correct linear term. So let's try 2 and 6 next, but eventually, we'll see that the linear term for that combination is also not correct. This means that we're down to our last option, so hopefully this option is correct. And when we do our double distribution with these numbers, we can see that we do, in fact, get the linear term that we wanted. Thus, our final answer here is x plus 3 times x plus 4. So let's circle that answer to indicate that we've successfully converted the original expression into the factored form. For our next example, let's try a problem that doesn't just have positive coefficients. This means that while we can still start with an x in each factor, we can't fill in the signs yet. Instead, we have to think back to our patterns and try to figure out how we can possibly get a negative linear coefficient with a positive constant term. Well, when our constant term is positive, there are really only 2 ways to make that happen. Either we were taking a positive number times a positive number, or a negative number times a negative number. And since a positive times a positive would result in a positive linear coefficient, let's try the other case and do a negative times a negative. Thus, let's put a minus sign in each factor, and then we can make a guess at what numbers will fill in the blanks. And since those numbers have to multiply to 24, we'll list out all the pairs of numbers that we can think of that multiply to 24. Also note that we're writing all of these options as negative numbers, since the minus signs in each factor can be interpreted as adding negative numbers. Then, let's make our first guess, and we'll go with -4 and -6. When we multiply that out, though, we can see that it wasn't correct. At this point, we could keep guessing numbers that multiply to 24, which will eventually get us our answer. However, as we do more examples of factoring, it might get a bit tiresome to be making several guesses for each question. So let's pause for a moment and see if there's a way that we could have gotten the correct answer on our first guess. Notice that when we chose -4 and -6, the coefficient of the linear term was -10, which also happens to be -4 plus -6. This was actually an observation that we made earlier when analyzing our patterns, but we haven't been using this to our advantage yet. At this point, though, we should be ready to take advantage of this information. So let's look back at our pairs of numbers that multiply to -24 and see what they add up to. And sure enough, -3 and -8 add up to -11, which is the linear coefficient in our desired result. This means that if we pick -3 and -8 as the constants in our factors, we should get the right answer. And once we double check that, we can see that they are indeed correct. Let's try utilizing this new piece of information in this example. We'll start off as usual with this template, and then we'll note that we want the constant terms of our factors to multiply to -33. This means that one of the numbers that we picked needs to be positive, and one needs to be negative. We'll list out some options for that here, and note that there's a difference between picking +3 and -11 versus +11 and -3, which is why we're listing out both options. Now that we have those options listed out, we just need to look for a pair of numbers that adds up to -8, and that seems to be the case for this pair. So we'll test this out by doing our double distribution on x plus 3 times x minus 11, which ends up being the correct answer. Then, for our last example on this screen, let's try out a problem that contains some small numbers. The only pairs of numbers that multiply to -3 are +1 and -3, or +3 and -1. And since we want those numbers to add up to +2, we'll go with the option where the positive number is larger, which is this one. Then, we'll check our work and see that our answer is correct. Moving forward, we'll check out some unique situations or special cases and focus our discussion on what makes each case special. But note that rather than developing special strategies for each special case, we're going to try our best to stick with our main strategy in each example. In this first example, it can be easy to get mixed up with the -x here. Just remember that when there isn't a coefficient explicitly written in front of the x, we can imagine that there's a 1 there. Thus, we're looking for two numbers that multiply to -30 and add up to -1, which is this combination. Next, we have an example that doesn't have a linear term at all. Thankfully, there's a way that we can rewrite this problem with a linear term, and that linear term will have a coefficient of 0. Then, we'll be looking for numbers that multiply to -36 and add up to 0. But the only way for that to happen is if we have a positive and negative version of the same number. And since 6 times 6 is 36, we can get the result we want by choosing 6 and -6 as the constant terms in our factors. Our next example once again has two terms, but this time we're missing the constant term. But similar to last time, we can rewrite the polynomial with a constant of 0. Then, we're looking for numbers that multiply to 0. That throws a bit of a wrench into our general strategy, since there are infinitely many possibilities for this condition. But remember that we also know that the two numbers we pick have to add up to 12. This means that 0 and 12 work as a combination. And since x plus 0 is just x, we can rewrite our answer this way. Then, when we check our work, we don't even need to do double distribution. We can just do regular distribution to verify our answer. Our last problem on this screen appears to be a pretty normal case, so we should be able to just list out pairs of numbers that multiply to 20 and see which pair adds up to 8. However, none of our pairs seem to be working, and it turns out that such a pair doesn't exist. When we're dealing with real numbers, there are certain quadratics that can't be represented in the factored form. This example is one of those cases, and so we say that this is not factorable. For our final screen of this video, let's continue to look at some special situations, starting with an expression that's in the vertex form. If we tried guessing at the factored form right away, it turns out that the strategies that we've developed and discussed so far wouldn't work, since those strategies were based on the standard form. Fortunately, though, there's a simple solution. We just need to convert this into the standard form first, and then we can convert into the factored form. In fact, this will be our strategy for any quadratic conversion problem where we aren't starting with the standard form. Just convert it into the standard form, and then convert to the form that we actually want. Our next example is also not in the standard form, so let's start by converting it to the standard form. Once we do that, we can list out pairs of numbers that multiply to 30, but we'll quickly see that none of those pairs add up to 4. So this is another example that is not factorable. Finally, let's check out these two expressions. We can factor these in our normal fashion, and we'll see that we can get a factored result for each expression pretty quickly. There is something special about each of these results, though, which is that they both contain repeated factors. This means that these are both perfect squares, so we can adjust our final answers and represent the expressions this way. That concludes part 1 of this video on converting quadratic expressions into the factored form. Hope you learned something new, and thanks for watching.